Welcome to Math with EJD. I've been talking about different root finding methods, you know, talking about bisection, secant, fixed point iteration, and of course, Newton-Raphson. And just like I've been saying, um, we have the following root finding methods, right? Root finding methods, especially for nonlinear functions. So broadly classified into 2-point methods, 2-point methods. So these 2-point methods require either two initial guesses or they require an interval within which the solution lies. And then we have 1-point methods. 1-point methods. So the 2-point methods are bisection. Bisection requires an interval. And the idea of bisection is you keep halving the interval until you find the root you're looking for. And then you have the secant method, which uses two initial guesses, talking about a secant line touching the function at 2 points. And then for the 1-point methods, we have a fixed point iteration, fixed point iteration method. And then we have the Newton-Raphson method, Newton-Raphson method. So we have considered all of this. So the essence of this video is to compare their performance across different metrics. For instance, imagine we look at the method, and then we have say the convergence. How does it perform convergence wise? Then we talk about complexity. Then we have reliability. And we have to shrink this to fit everything I want to consider. Reliability. Then we have key strength. So each of them have their key strength. And then key strengths rather. And then they also have their weaknesses. So that's the essence of what I'm going to be doing in this video. All right. So first off, let's talk about bisection. That's the first one we considered. Bisection method. Okay. So talking about convergence, we see that it can be very slow because it converges linearly. So that convergence is pretty slow. But the complexity, it is actually simple. It's simple. You just need an interval and then you keep, if you have not seen the video, you can refer to it in this playlist. So it is simple. All it requires um, is the interval requires interval. So it's either you're given the interval or you check the interval yourself by confirming that if you have 2 points A and B if the interval is AB, so check FA, FB. If the signs are different, that is one is plus and one is minus, then it means that the solution lies within them. So it's that simple. And talking about reliability, for the reliability, right? Guaranteed if roots guaranteed if roots bracketed. So the solution is guaranteed, right? Guaranteed solution for bracketed roots. What that simply means is that if you once you check once you check and you're sure that the solution lies within the interval, then you're guaranteed to find a result. Then the key strength is that it is robust and reliable. It is robust and reliable. So the key thing is be sure the interval you're working on, the solution is actually contained there. And the simple check is check the two values and see if they have opposite signs. That's all. The weakness is that it is slow and it needs bracketing. So you have to worry first of all to be sure that there's an interval within which the solution is contained. So that is that for bisection method. Okay, so if you have an interval, you may want to consider using bisection method. So let's talk about secant method. Secant. So for secant method, what is the convergence like? It converges faster. it converges faster. We are going to see all of that. We are going to look at the codes again, like, and see this convergence thing, the number of iterations in which they converge. So it converges faster. It is not linear, it is super linear. So superlinearity is faster than linearity. Then talking about the complexity, it is moderate, no derivatives. So it is moderate. It is moderate. Bisection does not require derivatives too. So moderate and no derivatives. Although it tries to approximate the derivative somehow. So it is moderate and no derivatives. Okay. Then talking about the reliability, it can fail for bad guess. So if you guess wrongly, you may not get your answer. Can fail for bad guesses. So you have to guess right. Okay. Then the key strength is that it is faster than bisection. Faster than bisection. Faster than bisection. Then the key weakness is that it may fail if guesses are far from roots. Failure for guesses far from root. So you have to be sure you are guessing something as close as possible to the actual roots. So that's the only guarantee. Then we can move on from there and talk about fixed point iteration. Fixed point iteration. So for fixed point iteration, right? Um, the the convergence is variable. The convergence varies. Interestingly, we saw a very good example. We had three different expressions, and then we saw that one converges and two diverge. So it actually depends on the function. So it on depends on g of x. So the kind of g of x we have will determine whether it will converge or not. Then talking about the complexity, well, it is actually simple, right? It is simple. You just express x as a function of the other parts, and then you begin to iterate. It is simple. So you may have to reformulate. Reformulation needed. So, I mean, in my case, I just give you so I think the first thing you want to do is get all the possibilities. So then try all of them and see which one works better. Then talking about reliability, okay, that's complexity. Reliability diverges with poor g of x. So it diverges with poor g of x. I mean, we saw that practically when I did that. We had three functions, but two diverged. And talking about key strength of fixed points, it is easy to implement. Easy to implement. Easy to implement. Then finally, the key weakness is highly sensitive to iteration function, which is the g of x. Highly sensitive to iteration function. And that is the g of x we've been talking about, right? Okay, then we talk about Newton-Raphson. Newton-Raphson. So for Newton-Raphson, right, the convergence is fastest. So it has the fastest convergence. As you can see from the code, that's the fastest convergence because the convergence is quadratic. So it has the fastest convergence because we are using both the function and its derivative. Then the complexity, it's actually complex. It's complex in that it needs derivative. Okay. Then talking about the reliability, it can fail for poor guesses. So you also need an initial guess, right? So can fail for poor guesses. Think just like Secant, I think. Then what about the key strength? It's extremely fast near roots. Extremely fast near roots. Extremely fast near root. Then the key weakness is that it fails if derivative is 0 or poor initial guess. Okay. So those are the key comparisons. Now, okay, I guess we can visit the code now. I mean, just to see the speed of convergence at least. So first of all, if you look at the bisection method, the result is implemented in 6 iterations. So of course, I've made sure the tolerance level is the same for all of them. So bisection does it in 6 iterations. Secant does it in 5 iterations. Fixed point does it in 4 iterations. So you can see secant is faster than bisection. Fixed point is faster than secant. Then Newton-Raphson also does it in 4 iterations. But I mean, if I think it's because of the initial guess, right? For most initial guesses, this actually will be faster because you can even see that this is closer because this is 1.521444146 blah and all that. Here it's 5211 521141. So this is still a bit far from the result. So Newton-Raphson is still the best of them all. Okay, so we have all of that going on like that. Now let's quickly do a simple conclusion as we in comparing them. First of all, we just take note that bisection is most reliable. Okay. Then Newton-Raphson is bisection is the most reliable. Newton-Raphson is the fastest. Okay. Then secant has balanced efficiency. Okay. And lastly, um, avoid fixed point iteration unless g of x ensures convergence. Okay, so you can make your choices based on all this information. So in all, the choice of method depends on the problem's characteristics, tolerance, and available information. Okay. So you may have a situation where you are constrained to use a particular method. So if you are constrained to use fixed point iteration, don't go and use Newton-Raphson because you are going to lose some points. So that brings us to the end of this subsection of numerical analysis, where we have been looking for the roots of nonlinear functions. Okay. So if you have not subscribed to the channel, there's a lot more coming. Don't miss out on that. Subscribe and hit the notification bell so you can always get alerted each time a new video is released. For those who have subscribed, thank you so much for that. Comment, let me know how helpful these videos are. Let me also know there's a topic you'd like me to teach or a problem you'd like me to solve. Then also let me like and share so that more people can have access to this great content. So like come your way again. Keep enjoying maths. Bye.